space, the final frontier. These are the voyages of the starship Enterprise. Its 5-year mission, to explore strange new worlds, to seek out new life and new civilizations, to boldly go where no man has gone before.
Good afternoon and welcome to Information Retrieval and Recommender Systems, and we're moving right along in our chapter on clustering. The last video that you looked at talked about agglomerative clustering. Today we're going to talk about KNN, as you can see written up there. First of all, a couple of things here. Let's just, a lot of this is all a vocabulary lesson. If you take a look at those two short PDFs I gave you, if you take a look in section 5.4.2, they talk about what are called the divisive algorithms. Of course, you could call a person divisive, and that would be very insulting, but when you're talking about clustering algorithms, you're not being so bad. Remember before, when we were talking about agglomerative, we were talking about bottom-up, meaning that we started off with each member in single clusters all by themselves, and then what we started to do was just group them together. So this was basically bottom-up. And what you do in divisive algorithms is you start off with the entire population and you do a top down. Okay, so you're starting with something big and you're trying to make them into smaller and smaller groups. Now, the thing that we are going to be looking at today, we're not going to look at all the algorithms that are mentioned in that chapter, although they're all very, very similar. We're looking at this thing called KNN. And KNN stands for K nearest neighbors. Okay? We will get to this in a second. Before we get to K nearest neighbors, I want to talk about something else very quickly. I want to talk about something called a centroid. Versus something that's called a medoid, or a medoid. I would say it medoid. But I think the easiest way to demonstrate this would be as follows, and I'm going to do it in one dimension. I want to assume that I have a set. And let's assume that this is 0 over here. And this is 10 over here. And let's assume in this set, I've got the value 1, and I've got the value 2, and let's assume I have the value 4, and I come over here, and I have the value 8, and I have the value 9. So first of all, as a set, I want to say that I've got 1, 2, 4, 8, 9. Now, again, if we want to, we could think of this as being a cluster. That's fine. The question is what would be a nice representative name for this cluster? And there are a couple of different ways that we can do this, and one is called the centroid method, and one is called the medoid. Now, the centroid is very simple. That if we were to let this be a set S, what we would do over here, we would come over here, and we'd go from I equals 1 to 1, 2, 3, 4. There are 5 elements in there of S of I. For S of I contained in S. And we would divide this by 5. Okay? And this value over here, we would call this the centroid. Okay, in other words, it's the average of all of these numbers. And if I were to come in over here and figure out the average of those numbers, 1 plus 2 is 3, plus 4 is 7, plus 8 is 15, plus 9 is 24, and that's all over 5. So that's 24 over 5. And that means that the centroid is equal to 4 4/5. So if I were to come over here, right about here someplace, that would be the centroid. Okay? And some people would say, gee, if I wanted to give this thing a name here, I'd give it the name 4 4/5. Name, whatever that means. We'll talk about that later. Okay? But now there are other people that feel that if we are going to pick a representative name for this cluster, it should be an element of the cluster. So we would come over here and we would actually look for which one of these things is closest to the centroid, and the answer is it would be this number 4. That is the medoid. So the centroid is the actual average of all the numbers in a set. The medoid is the element in the set that is closest to the centroid. Now, I just bring that up because there are different clustering algorithms employed in this section here that make a distinction between these. When we're talking about the k nearest neighbors, we're going to be looking at the centroid. There's another algorithm talked about in this section here in this 5.4.2 divisive algorithms. There's something called PAM. And PAM stands for partition about medoid. It's a very, very, very similar algorithm to the KNN. It's just what is it that we're trying to get near. Now, I want to suppose, let's consider just another example here. Suppose I have a set S, and S is comprised of points in 2 space. -1, -2. And the question is how do I find the centroid of this? And the centroid of this is actually very simple. I'll call it X, I'll call it C, is equal to the sum of the xi's, 1, 2, 3, 4, divided by 4. And I'm going to have that yc is equal to the summation of all the yi's divided by 4. And the centroid here would just equal the point xc, comma, yc. So for example, I'd come over here, xc is equal to 1 plus 3 plus 7 plus a -1 all over 4. So that is 4 plus 7 is 11, -1 is 10. This is equal to 10 over 4. And y sub c is equal to 2 plus 4 plus 6 plus a -2. And let's see, 2 plus 4 is 6, 6 and 6 is 12, -2 is 10 over 4. Oh, look at that. So it turns out that the centroid is equal to 10 over 4, comma, 10 over 4. Okay? Okay, so what is this algorithm that we call KNN? Well, the goal of KNN is to partition the data. I'm going to say partition data D, which is equal to D1, D2, D3, all the way up to D sub n, into K clusters that I'm going to call C1, C2, C3, all the way up to CK. Everybody okay with the notation so far? Such that and here I'm going to have to take a little bit of a diversion. Okay? And the diversion is first of all, we're going to assume that all of these points are in some dimensional space. They're in some RM space. Okay, this could be in 2 dimensions, 5 dimensions, 23 dimensions. And I want to introduce a little more notation here. Each one of these clusters here, with it, I want to associate a centroid. So I want to say that the centroid of cluster CJ is, and we're just going to call it CEN of CJ. Okay? And remember, the way that we would find, given a cluster here, the way that we would find the centroid is just by doing a calculation similar to this one right over here. Okay? So what is the goal of KNN partitioning or KNN clustering? Well, it's to take all of these points and put them into K clusters such that when I come over here and I look at the distance, okay, I look at the absolute value or the distance of sen CJ minus, and I'm going to say DJI, okay? When I look at this squared and I sum this over all D sub j i's contained in CJ, and then I sum this over all C sub j's, that this quantity right here is minimized. Now, think about what this is saying here. What I'm doing is I'm looking to put all of these into the cluster, into a specific cluster, so that when and maybe this would be best demonstrated with a drawing. Let me give you an example here. Here are some points in a cluster. And I'm going to draw a line. Here's the cluster. This equals the centroid. Remember, that's not necessarily an element in the cluster. And then I come over here, and here's another cluster. Okay? What I am doing is I am saying I want to calculate this distance and square it. 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 So what that is corresponding to is this inner summation right over here. In other words, what I'm doing is I am summing up all of the distances of the points in the cluster from its centroid and squaring it. Likewise, I'm doing the same thing over here. Okay? And then what I'm doing is I'm adding up the number for the sum of the squared differences here, here, and all of the other different clusters. So that's what's giving me the double summation. See, this is the summation within any one particular cluster. And then this summation over here is saying, let's sum it up over all the clusters. And what it's doing is it says I want to form these clusters in such a way that this whole thing is minimized. So I'm going to describe the algorithm to you now. We haven't done that yet. The other thing that you should be thinking now, and this is a big issue with this algorithm, is what is K? Is K 3? Is K 23? Is it 5? Is it 500? And that is an excellent question. There is no answer. And we're going to talk about the problem with determining K. But the point is what we're doing for this particular algorithm is we're assuming that K has already been given to us as a parameter. Everybody okay? All right. So how does this go on here? So first of all, I want you to recognize the following. Remember, we said that we have D is our population, if you will. So D is equal to D1, D2, all the way up to D sub n. And the first thing I am going to do is I am going to randomly pick K elements. Okay? Randomly. Doesn't matter how you do it. And what I am going to do is I am going to form K clusters each with one of K elements picked. So that means now I've got these K clusters, and I'm going to call it C1, C2, C3, all the way up to CK. And each one of these is comprised from one of these elements here. In other words, these K elements form K clusters. Each cluster has exactly one element in it. And remember, for each one of these clusters, we can also figure out the centroid. We can figure out this thing called CEN of CI for each one of these. Everybody okay with that? Fine. Now what I'm going to do is I go for, let's see, I'm going to say for J equals 1 to N, I'm going to say pick D sub J. So in other words, I'm going through every element in my population here, starting with the first one and all the way to the end. And then what I'm going to do is I'm going to say pick. I'm going to say pick CL such that the centroid of CL minus DJ, that distance is minimized. Minimized. In other words, I think I have one more page here. In other words, initially, here are my 5 initial clusters. And you could, if you want to, you could think about them. They're looking like this. Of course, they only have one element in them. And now what I do is I am going to pick my D sub 1, whatever that happens to be, and maybe it's right here. So if it's right here, I'm going to calculate this distance to this centroid. I'm going to calculate this distance to this centroid. I'm going to calculate the distance to this centroid. I'm going to calculate the distance to this centroid and the distance to this centroid. And I'm going to pick the one of minimum distance. Well, the one of minimum distance is this one right over here to this centroid. And what I'm going to do is I'm going to add this point to this cluster. So now this cluster now has two elements in it. And what I'm going to do is I'm going to recompute the centroid. And the centroid, of course, would be someplace over there. And now this cluster actually looks like this. And that's basically the algorithm. So what I'm going to do is I'm going to pick C sub L such that the centroid of C sub L minus this element is minimized. Then what I'm going to do is I'm going to add D sub J to C sub L. Or I'm sorry, I'm writing this all wrong, to C sub L. And then I'm going to recompute the centroid of C sub L. Okay? Now I'm going to do this for every element inside of here. So first of all, when I do it for every element inside of here, when I'm all done, okay, what's going to happen is all of these elements are now going to be assigned to one of these K clusters. Okay? But what I can do is I can repeat the process all over again. And what's going to happen is I want to keep track of, I want to keep track of this quantity right over here. And what's going to happen is it may be the case, and I guess I'm going to need some more screen here. Let me see. Yes, I am. So at this point, I have to come over here and do this. Don't have nice, wonderful yellow paper anymore, but that's okay. I mean, what may happen is I'm all done, and I may have a situation that looks like this. So here's a cluster here, and here's a cluster here, and here's a cluster here, and here's a cluster here. And what may happen is it could be the case that there's the centroid there, and here's a point here, and here's a centroid here. And it may have been at the time that when I added this point to this cluster here, the centroid here could have been someplace else. But now as we look at it, we can see that this point here is actually closer to this centroid. In other words, the point that I'm trying to get at is that if I run through the points again, after going through them all once, and let me find the slide here. I apologize. Things are getting a little crazy. There's 2. 1, 2, 3, 4. What happened to 5? I'll find it. Is this it? No. That's not it. Oh, I think it's behind the screen here. There it is. It's right there. In other words, what's going on over here, this is just one iteration through all of the points. The next time I go through the points, I could go through them a second time, and it may be the case that a point is going to jump from one cluster to another. Okay? It may be the case that moving from one cluster to another is going to reduce that total error that we calculated. So what happens is we keep doing this process over and over again. All right? So we keep repeating the process. Hang on here. We keep repeating. Well, repeating what? Repeating what? Go through all elements. And reassign clusters. And then the question is, well, for how long? And the answer is, well, we're not so sure. Okay? Now you could say, do it a fixed number of times. $20, $30, $50, okay? Or you could do it do it until the improvement is small. In other words, you say, gee, I've gone through all the elements and the change in minimizing that error was less than 0.5, or it was less than 5, or some number that you determine. You say at that point, stop. In other words, we'll never know exactly if we've gotten to the minimal one, okay? But you can do either one of these things over here and get some useful results. Now, that's basically the algorithm. It's very simple. There is, some people have a criticism of this algorithm. And the criticism is it's not deterministic. Well, what does that mean? Well, it means if we repeat, we may get different results. And why is that? And the reason for that is because if you remember the way we started the algorithm said randomly pick 10 points. Well, if I do k-means clustering 10 times, I'm going to pick 10 different points each time I run it. That could lead to slightly different results. But in general, the results turn out on average to be very, very, very similar. So this is a very, very useful algorithm. As part of your homework, you're going to be reading a paper where they employ this. One of the questions that they talk about is how do you go ahead and pick a suitable number k? And I will leave that up to your reading. Okay, that is the end of the discussion.